So these are all examples from old AP exams, most of them fairly old, but these questions still get asked. And the reason I left the numbering on them, if it's a high number for a multiple choice question, that means you can use a calculator on it. If it's a low number for a multiple choice question, you cannot. So this first one, although you can use a calculator on it, it doesn't do you any good. Only about half of the problems on the calculator section really need you to use a calculator on them. Part of what they're trying to test there is, do you know when to use a calculator and when to not bother? Okay, so we have this function f that's continuous from -2 to 2. Notice immediately my brain goes, hey, what did it not say about it? It didn't say it was differentiable. It just said it was continuous between -2 and 2. And it says that f of -2 and f of 2 are both 0. All right, so I'm a very visual person, so I usually draw a really quick and very sloppy graph. It doesn't have to be anything, but I know nothing about how this is connected. It could be connected by a nice smooth curve. It could be connected by like a sawtooth thing. It could be like a absolute value function that's been shifted up or down or something. There's all kinds of things that it could be. So, maybe it's just a horizontal line that connects them. Maybe it's something nice and smooth. Maybe it's not so nice and smooth. Any of those are possible. Okay? It says there is no c between -2 and 2 for which the derivative is equal to 0. Well, that immediately means it's not this one, is it? Because the derivative there was 0 all the time, and it's not this one either. All right, so let's take a look at what we have left. Between -2 and 2, the derivative is always positive, followed by the derivative is always negative. Well, I drew something. Is the derivative always positive or always negative on this? No. If it was always positive or always negative, the function would either be always going up or always going down. It can't get back to 0 if you don't switch directions somewhere. This one says f prime always exists. Well, does f prime exist at this point? Nope. This one also says f prime exists, but it's not continuous. Well, the derivative doesn't exist there. There's got to be a place where the derivative does not exist. So it is choice E. Now, that doesn't sound much like the mean value theorem, but the reason I wanted to show it to you is because this is one where students sometimes when they read this, they go, it's continuous, and your brain just keeps going and says, and differentiable, but it doesn't ever say that. Okay, and it says there is no place where the derivative is 0. Where'd they get 0 from? Well, the average rate of change on this would be 0. Started at 0, ends at 0, average rate of change, 0. All right, this next one is another calculator one. This one, you look at the answers and you immediately know you're going to need a calculator for it. It says, let f be defined by the function f of x is equal to x plus the natural log of x. What is the value of c for which the instantaneous rate of change at x equals c is the same as the average rate of change of f over the interval from 1 to 4. Okay. Notice it doesn't say mean value theorem anywhere in here, but that's what they're doing. Now, we should at least quickly go, okay, does the mean value theorem actually apply here? On the interval from 1 to 4, is this always defined? Yeah. Where is natural log of x undefined? 0 and? What can you not take the logarithm of? You can't take the logarithm of a negative. Exactly right. You can't take the logarithm of negative. How do I know that so quickly? Because I know what the graph of natural log looks like. I'm not big on memorizing a lot of these, but if you know what that looks like, you go, oh yeah, that's not defined over here. Okay? It's also helpful because you go, oh here, look, this is 1, 0. Knowing just that much of the graph is very helpful. All right. And then the derivative, let's check that out. F prime of x is going to be 1 plus 1 over x. Where is that undefined? At x is 0. Is that a problem? Okay, I'll wait until you decide.
Yes, because the fraction can't be, the denominator of the fraction can't be 0.
Yes, however,
There's a 1.
pardon?
There's a 1 as well, so it doesn't matter.
No. Look at the interval. Yes. Conspicuously absent from this interval is?
Oh, 0.
0 is not in this interval, so it's not a problem. On this interval, the derivative is always defined. All right, so the instantaneous rate of change, well, that's this, is equal to the average rate of change. Well, the average rate of change is going to be 4 plus the natural log of 4 minus 1 plus the natural log of 1 all over 4 minus 1. It'd be nice if we could simplify that a little before we even try to do anything with it. And you definitely don't want to put that into your calculator. The denominator clearly is 3. The numerator, we're going to have 4 plus natural log 4 minus 1. Okay, so that's going to be 3 plus the natural log of 4. And what's the natural log of 1? 0. That's what I was just showing you here. That's a little more compact than this thing. And we want our instantaneous rate of change to be equal to that. Okay. So 1 plus 1 over x is supposed to be equal to 3 plus the natural log of 4 all over 3. You can spend a lot of time trying to work this out to make it nicer and try to solve it for x and then put it into your calculator. It's a complete waste of time. At this point, you should just move everything to one side, set it equal to 0. So 3 plus the natural log of 4 over 3 minus 1 minus 1 over x needs to be equal to 0. You could have left it in this original form, but that's just more to type in, more places where you could go wrong. I do simplify when simplifying is easy. When it's not, I don't bother. So y equals, clear this out. Alpha y equals, so I get a nice looking fraction, 3 plus the natural log of 4. That way also, if I forget to close a parenthesis, it's not as big a deal. Minus 1, minus, and just to make it look pretty all the way around, 1 over x. And I want the interval from 1 to 4, so my window, I wanted to set that from 1 to 4. And I'm looking for where this is 0. So I'm going to tighten up the y window to just go from -1 to 1. All right, well, I clearly have A0. It's a little bit more than 1. And I'm not even going to bother putting that into my calculator because there's only one answer choice that fits that. Now, should you probably check that? Yeah. But I'm going to do it by just tracing to 1.244. And the y value is pretty close to 0. Hang on.
Oh, I think it's going across right next to the 2.
I'm sorry?
You set the window from 1 to 4, so that would be...
Oh, that'd be 2 point something. Yeah. See, that would have been dumb. 2.164. And you get something that's incredibly close to 0 because that's times 10 to the negative 6th. So it's not that answer choice. Thank you, sir. 2.164. All right. Let's move on to some free response questions. This first one is a question number 3, which means, yes, you can use a calculator on it. I've skipped a bunch of other parts of this question because I don't want to do the whole free response question. I just want to do the part that involves mean value theorem. So we have a continuous function f that's defined on the closed interval from -4 to 6. So this function is continuous on the entire interval. The graph of f consists of a line segment and a curve that is tangent to the x-axis at x equals 3 as shown in the figure above. On the interval between 0 and 6, the function is twice differentiable, where the second derivative is always positive. Well, and that matches what we would have guessed because this appears to be concave up, right? So the second derivative would be positive. Is there a value of a between -4 and 6 for which the mean value theorem applied to the interval from a to 6, okay, so I'm going all the way to this end, but where I'm starting hasn't been determined yet, that guarantees a value c between a and 6 for which f prime of c is equal to 1/3. And you're like, where the heck did 1/3 come from? All right, well, this is an instantaneous rate of change, right? The mean value theorem says that on some interval, the instantaneous rate of change is equal to the, what's the other part supposed to be? The average rate of change. So I need to look for a place where the average rate of change is 1/3. One endpoint has to be over here at 6. Where is there a place where the average rate of change is 1/3? At 3. Because the slope of that line is 1/3. So we have to justify our answer. So first we have to say, on the closed interval from 3 to 6, f is continuous, and on the open interval from 3 to 6, f is differentiable. It told me that it was a continuous function, and it told me that the function was twice differentiable, which means its first derivative exists and its second derivative exists. So First, we need to make sure that the conditions apply on this interval. Yep. The average rate of change of f on the closed interval from 3 to 6 is 1/3. So the mean value theorem, which you can feel free to abbreviate MVT, everyone will know what you're talking about, guarantees a value of C where 3 is less than C is less than 6, at which f prime of C is equal to 1/3. And I know sometimes the wording of these can be hard. As much as possible, there's a technique called parroting, which is where they say something, you say the same thing back in the same order. So do you notice how much of this is exactly what they said? Guarantees a value of C. All I did was change the A to 3, at which f prime of C is equal to 1/3. Okay. Notice, do they ask you to find the value of C? No, they don't. Sometimes they will, but on this one they didn't. Questions about that? This is a tough question. Partly because you have to make the leap of going, oh, I know that this is the average rate of change, and I can see right here the only place where the average rate of change is 1/3 is from 3 to 6. That's the step that many students didn't make, and then they basically got no points for this part. Now, just because you get shut out on a section of a free response question, don't let that bug you. Sometimes it'll be part A and you get shut out of that. Although A is usually the easiest part, B is not always the next easiest part. Sometimes B is harder than part C. All right, let's look at this one. Again, this is one you could use a calculator on. The functions f and g are differentiable for all real numbers, and g is strictly increasing. All right, notice if f and g are both differentiable, what else does that tell you about f and g? They're continuous. The table above gives values of the functions and their first derivatives at selected values of x. The function h, and this is what made this question difficult. Suddenly now we're doing a composite function. H of x is equal to f of g of x minus 6. Explain why there must be a value c between 1 and 3 such that h prime of c is equal to -5. All right. Again, anytime you see this kind of stuff, you should be immediately thinking, oh, that kind of looks like the end of the mean value theorem. So I want to look at what happens on the interval from 1 to 3. But first I need to talk about, does it meet all of our qualifications? Well, since f and g are differentiable for all real numbers, h of x, which is f of g of x, minus 6 is also differentiable for all real x, and therefore continuous. So we have to first talk about the conditions of the mean value theorem. We didn't just do it on 1 to 3 on this case. We said it's true everywhere. So we can use any subinterval we want. You don't have to put this phrase because you have done all the work, but you can say it, therefore the MVT applies. Sometimes if you've worded something a little sketchily, but you include that, they're like, okay, they do know they're talking about the mean value theorem. So I need to find the average rate of change of h on the closed interval from 1 to 3. And we're really hoping this comes out to be negative 5. Is, so f of g of 3 minus 6 minus f of g of 1 minus 6 all over 3 minus 1. Well, let's see. G of 3 is 4. So this is going to be f of 4. Oh, and notice I've got minus 6 minus negative 6. That's going to drop out. So it'll be f of 4 minus g at 1 is 2. So that'll be f at 2 all over 2. So f at 4 is negative 1. F at 2 is 9. All over 2 is negative 5. So there must be a value of C for 1's less than C, less than 3, such that h prime of C is equal to negative 5. So again, this one doesn't mention the mean value theorem, but that's exactly what you're using. Let's see. We're not going to be able to get through all of these. Let's look at number 3 on the next page. So a metal wire of length 8 centimeters is heated at one end. The table above gives selected values of the temperature in degrees Celsius of the wire x centimeters from the heated end. So at the heated end, it's 100 degrees Celsius. 8 centimeters away, it's cooler. It's 55 degrees Celsius. The function t is decreasing and twice differentiable. Okay. First it says estimate t prime of 7. We did this day before yesterday, I guess. how could we estimate t prime at 7?
The values around 7, so 6 and 8.
Right. So what will we do with those?
Average rate of change.
Okay. So that would be, how would we write that?
55 minus 62.
Mm-hmm.
Or 8 minus 6.
Yep. And by the way, if this were an actual AP exam, I would stop writing on that part of the problem right there. Because the only thing that can happen from here is that you can make a mistake and lose the point that you just gained. You don't gain any points by simplifying numeric answers. Okay? But you can lose a point if you simplify it wrong. Now, if this is a homework problem, you want to go ahead and do it. Right? But if this is an actual AP exam, there is no reason to continue working on that. All right. Next part, are the data in the table consistent with the assertion that t double prime of x is greater than 0 for every x on the interval from 0 to 8? Explain your answer. And I tried to pick, honestly, I picked out some of the nastier problems for these. This one torched students. And fair enough, it's hard. You're like, wait a minute, t double prime? How am I supposed to know anything about that? They were trying to lead you in part A to help you with part D. Because what we can find are the average rates of change on each of these intervals. So, the average rate of change of t on the closed interval from 0 to 1, the temperature decreased 7 over 1, so that's negative 7 over 1, or just negative 7. The average rate of t on the interval from 1 to 5 is 23 over 4. Sorry, negative 23 over 4. Which is what, negative 5 3/4? I think it makes it easier if you make it a mixed number to be able to compare them. The average rate of change of t on the closed interval from 5 to 6 is negative 8. Now, before we keep on going, let's take a look. If t double prime is positive, that means t prime is increasing. Well, from negative 7 to negative 5 3/4 is increasing, but from negative 5 3/4 to negative 8 is decreasing. Okay? So it is not, but you'd have to write some more to explain that. All right. Y'all have a great weekend. Try and stay dry.